Okay.
Okay, so welcome back to the fourth and last session of the OCaMl workshop, and it's my pleasure to introduce Oleg Kiselyov, who's going to tell us about MetaOCaMl.
Okay. So a little bit about background of this talk. So this paper was written for myself. So I was implementing, making a new release of MetaOCaMl, which was released in May. And I thought about some optimizations which sounded too good to pass on, but it was also weird, and I will show you. So there's a doubt: is it actually, valid or not, working out or not? And so I kind of wrote some equations, some rules, and to convince us actually the types work out and it's type preserving and so forth. So that's why I wrote the paper, and and then I thought, well, I have to come to ICFP workshops anyway, so I might as well, write, a little bit explanation and introduction and submit to a OCaMl workshop. So, one of the reasons is that, after all, the theory of MetaOCaMl, how it actually works, hasn't been written down. Well, there is a paper by Taha and Quarters, but it's, obsolete, and so it doesn't correspond to the state of the art. So, might as well write something down. And, well, to say that the first time I heard the word MetaOCaMl, it was in ICFP 2003 in Pittsburgh at a lunch with Walid Taha. At that time, MetaOCaMl wasn't actually publicly known. It was kind of internal project of Walid. And so I got, since that time was involved. So I think 20 years is kind of a good time to reflect and, how it could be done and how it could be done better and what's the benefit of hindsight. Well, because it's like 22 minutes of presentation, that I don't think that I have enough time to, for reflection. But hopefully I have time to make a different point that somewhat unexpected to someone maybe, is that the formal notation, that Greek notation that we all, at least some of them get used to, it's actually pseudocode. So you kind of think about in the papers you read is a very theoretical papers with a lot of Greek letters and so forth, but think about it as the code, not as the some kind of mathematical notation. It is a pseudocode, and I hope to illustrate it. So actually I tried to illustrate in the paper, but it, based on the reviews, it seems to be didn't quite work out. with the reviewers. So maybe during live presentation would be more successful and convincing. So well. Perhaps I need to say what MetaOCaMl is. So in one sentence, it's a superset of OCaMl to assuredly generate code that has well typed, well scoped, and well formed. Well, I do it. The sentence I write so many times that I almost memorize it. But in short, so if you generate code in MetaOCaMl, it assuredly compiles. So it would be no type errors, and it would produce executable. So there's some static assurances. So I mentioned there is a code template, so brackets and escape. So what they are. So here is the code template. It's code enclosed in brackets. So you can think about brackets as if it were quotations. So like string quotations. So it's a value, and contains code to be generated. But unlike quotation, which, inside the quotation mark, you can put basically anything except another quotation mark. Here the code is, structured. What does it mean, structured? It has to be actually valid OCaMl code, and not just well-formed OCaMl code. It actually should be well-typed OCaMl code, and it's checked. So when you enter it in MetaOCaMl interpreter, for example, or compile, then it would, type check that it's int. And the code itself has, the whole bracket has a type int code. So it's an expression, generated code that, has type int. And when you eventually compile it, that it would give you type int. So brackets are the only one thing, and the second one is that what squiggle, which is called escape. Or you can, if you Lisp, then you think about anti-quotation. Right, so together with this variable, you can think about it as a code template with a hole, when x is a hole, and see how, on the hole filled in. So we have this previous code. we apply to this CH, and by performing application, it's kind of, you can see that hole gets filled in with this code. So, well, template ways of generating code is very popular, like in JavaScript and so forth, so forth. So MetaOCaml is multi-staging system. So these quotations, they may nest arbitrarily. So this is one example, and this is another example. So, and you can see by the type, code, code. So it's actually, so in a sense, it's a generating code that will generate code. And you can nest, arbitrarily. So we've seen there is a brackets and there is escape. But in MetaOCaml, there is also, well, there is a run, there is a cross-stage persistent, there is a gen-let rec, and et cetera, et cetera. So there are more facilities, but unfortunately, at the time doesn't permit me to talk about this, so I'll just skip them. So we talk about only brackets and escapes. One thing it's worth mentioning, which expression appeared already before. So here is the code of the function, and here is an escape, and within the escape, you can see there is this red X. So it's a code, but of X. So it's actually open code. It's a free variable, right? And you can evaluate. So putting using our previous CH. So the templates get filled with the X. So the free variable is, is a value, and you can manipulate open code. And as you can see, before that, we used kind of for the well, here it is, examples. The whole was a variable, right? And so in sense, the expression that we, fill with a call computed somewhere outside. But here we cannot replace it with a variable, right? Because the evaluation happens, so to speak, inside the scope of X. So with the staging, the evaluation and scoping happens in kind of weird ways. Okay, so as I said, this kind of theoretical, seemingly theoretical looking paper, and well, this is a, thing that, you can see in any theoretical paper in programming language. Well, hopefully, that shouldn't be too scary because it's a completely standard, simply type lambda calculus, which is the, well, model for, well, later on we add staging, but so far it's completely simple, as a standard thing, so there is nothing to even wonder about, but there is a little bit maybe unusual. It's the typing judgments, ET. So what, why I wrote in an unusual way is to emphasize what the type checking is essentially type reconstruction. So we have untype expression, which is, well, integer X application, variable application on lambda. And after the type checking, we, add type, convert it to types. And why it's written this way? Because, well, as I said, this is, it's not Greek, it's actually pseudocode. So that's how OCaMl works. So E is, well, AST, which is called parse tree. And this, annotated, it's called typed tree, annotated. So the type checking in OCaMl converts from parse tree to type tree. And to show you, so this is the OCaMl type checker. It's a part of the OCaMl. It's called typecore. It's a very long file. It's 6,000 lines, but it's only part of type checker. There is some more stuff in OCaMl. So here's the function, which is one of the main. It's called type expect. So it takes the environment, which is, well, gamma on the slide, as expression as a source code expression, which is a parse tree. And, well, there is some other things, and it creates the typed tree. And here that first example, so that's the rule which you saw. So if the parse tree was I, or constant literal, then there would be create the typed tree, the same constant annotated with type. And that's how it is in code. Well, so this is a CST, there is some constant, then it gets, type of it. And so it creates expression descriptions, the same constant, and, well, gets the type will be integer depending on the constant. So it indeed creates from px constant, which is a parse tree, it creates what's, I mean, RUE, which is later creates the node, well, TX constant. So from path tree to type tree. So, well, let's take another example, the application. So it's for the application, so we see that there is a function, and it has to be a function type, and the argument should have the type T prime. And, well, if you see in OCaML, it would be, okay, so there is a special for type application, and it's, well, a little bit involved. There are much stuff, and to make it a little bit, let's look at one particular. Oh. Okay, so there is a type args, and the type args. So it's this is the arrow type. So so it looks at the type of the operand. So the type of the operand has to be arrow type. There is a type which is has to be from argument type, and there is the function type. And then after a while, it goes to type argument. So this argument, environment, and this type. It checks that this. So basically, well, I mean, I know essentially what this rule says, but as you can see, there is some, I mean, other stuff going on. So it's a much more concise notation as to what's going on. So, but of course, we're interested in staging. So what to do, I mean, how to add brackets and escape. So we add in our calculus brackets and escapes. So we add some type, and we need to have a type system. So fortunately, people already, I mean, worked out what the type system should be. And it turns out it has to depend on stage, which is the level nesting of brackets. So if outside the brackets is 0, so inside of brackets is 1, and if you nest brackets, then it becomes there. So everything becomes nested, and I mean, indexed by stage. And when you put an environment, then variables also indexed by stage. So the rules were well worked out in work by Sheard and Taha a long time ago. So they look something like that. Again, this is a pseudocode. So you can see, and I mean, all indexed by n. So how do we, I mean, so this is kind of pseudocode. So how do we implement it? Well, we can think, I mean, two ways implementation. You can think about this n is kind of the part of an environment, and we just, I mean, put something n into the environment, which I kind of thought. But another thing, like in the rule for the application, so n comes in here and propagates, I mean, to both sides. So it acts as this environment, right? It's, I mean, propagates from one application to another. Well, I mean, in this pattern, so it's like environments. One way of implementing is using global variables, right? So, I mean, it's a shallow, actually, implementation of dynamic binding using shallow binding. So if you use a global variable, then we don't actually need to do anything from these rules, right? Because, well, I mean, these rules don't do anything with n. So, which is a good news. So, if you want to add staging to OCaML, or I mean, MetaOCaml, for those rules, well, I mean, we saw how much, I mean, how long a type checking application takes, and the news that we don't actually need to do anything about it is a very good news. And most of the other rules are of the same kind. So we don't actually, after we, I mean, add this n, I mean, as a global variable, we don't actually need to do anything. Well, we do need to do something, for example, for function. We need to put, I mean, when enter the environment, we need to put, I mean, annotate with n. Well, that also can be done. So, okay. So the, okay, let's see if I, okay. Okay. Okay, later on. So that also can be done, but I mean, when we put things at the environment, we just need to, put n, and fortunately, well, in OCaML there is a attribute, and so we have, a way to put this n into the environment. And when we checked for the variable, so there is some condition, so it's there. Well, remember that when we put variable in environment, it's some kind of we have to annotate with a with its stage. Okay. And in a code, so this is the part that deals with the variable. So indeed, I know how it's done in MetaOCaml. So we get from the val attribute, so it's take from the environment. So it gets from the environment, we obtain looking and identifying the environment, obtain what's the description path, obtain this value attributes from which we extract the stage, and after some, some things. Okay, where is it? Okay. Doesn't actually show. Okay, here it shows. So we check if the stage of the identifier, if it's bigger than the global stage, then we report an error. So otherwise, so indeed, that this rule matches. It's a kind of pseudocode of the actual code. Well, but how to deal with brackets and escapes? Well, there are rules for dealing with the brackets and escapes. Typing rules are kind of very symmetric, so the bracket raises the, so the brackets has to be type checked in a, kind of at the higher stage and escape lower stage. But what the rule says is that here's the parse tree, so has a brackets annotation. But here we get the typed tree, and it also has bracket, right? And the same escape. So after we've type checked, we get brackets and escapes in the typed tree. And if we pass this brackets and escapes in the parse tree, then, well, the compiler doesn't know what to do with them, how to compile with them. So what to do about it? Well, you, eliminate it. This is also kind of the standard thing. So translate it away. And here are the example of, let me remove the types. Easy to see. So if we have this example of the typed tree, well, remove the annotation. So we translate it into using some parsing combinator. So MKL, which creates lambda, so creates the code. And here a more complicated example, and the combinators that create code, for example, MKL creates, given the, well, make application gives them two pieces of code, creates piece of code that contains application. Well, but how to really perform this translation? So, well, here, this is kind of improved the translation, which was in the original MetaOCaml papers. So here we take the type tree and apply the translation and translate it away. And there is some kind of that first part is most identity until we get the bracket, and until we 3 minutes, right? Okay, so until we get to escape, until we get the brackets, and then introduce the combinators. But there are some weird things into this translation. Well, one of the kind of for the performance reasons. So if we translate the application, then, well, it's kind of identity, but it's not actually, well, identity. Operationally, we have look at the tree and we reconstruct the node of the tree, right? So that's not what we wanted to do. So if compile the whole program, and then we can have to rebuild the whole tree. That is kind of, not very good, especially if it doesn't actually have any quotations. So, but we still rebuild the tree. So that's bad things. Another thing that's interesting that X at type T gets translated to also X, but at different type, which actually doesn't depend neither at M nor at of N, which is kind of weird. And lambda is also translated, also lambda, but at a different type. So is it actually even correct? Well, after contemplating this, here the optimized translation, which is, that's what I said, weird. So we, to remove the identity, this translation, so the translation and brackets away and type checking is now interleaved. So the rules, the previous rules for bracket replaced by these two new rules, where, if it says bracket at the level, it performs a translation, which is described below. If it's a higher level, it also performs translation. But somehow it doesn't, it introduces escape for some reason. And if, one of the weird things, it turns out it needs escape, but it doesn't need bracket in a typed tree. But the translation eventually removes escapes. Yes, it kind of sounds weird whether it really works, and that's what the paper was written, and there is some theorem that says it's actually types preserving, and also all escapes gets eliminated. So after, all things are done, we get the type tree that doesn't have need escapes, well, it doesn't have bracket at all, and therefore we can just pass it to the type checker, to the code generator, and, generate code. Okay, so I'm almost finished. So we, kind of come to questions, and I have one question to the audience. It has been long time noted that it's very hard to find any practical use for more than one stage. And that was noted 20 years ago, and I still couldn't find any compelling example. So if everybody noticed why we need more than one stage, it would be nice, because otherwise, maybe I shouldn't even maintain it. So, okay, so it was implemented, all the translations implemented in OCaML. And, translation is weird because it kind of, to support multiple stages, it looks like it only needs two, effectively. Okay, thank you.
Okay, do we have any questions? So I have a number of questions.
Okay.
So I'll ask one.
Okay.
So you've shown us this relatively compact translation based on this little calculus. But you've implemented this in OCaML. How far does the translation extend? Like, how much of OCaML does the translation extend to?
Okay, well, that's actually, thank you for, a very good question. Let's see if I, okay. So that translation which I showed is, okay, so type checking MetaOCaml construct. So here is the MetaOCaml escape. And, okay, to remind you what, so we translate, so these two rules, right? And the code, well, that's what the code is written, and it basically, in a, well, the way I wrote the code is, well, I had these rules, written and printed on PDF, and I put this piece of paper before me, and looking at the piece of paper, I just type it in what, the rule says. So it was written, just translating those rules which are, there. Yeah, you can, check the stage, and then the global stage one, you do some one thing, otherwise you do some, so. Well, well, that's essentially is, you add to, that's a type checker, and then there's other things on translate and escape. Generates, does perform translation and adds escape to the, to the top. So, but that's kind of outside of the, so to speak, the type checker. So the extent to the type checker is actually very minimal.
I think we have time for one more.
Yeah. Yeah, this morning we have a talk regarding the macro OCaMl. So I'm just wondering, could you comment on what's the difference and similarity of your work and that work? And do you see there's a unification path, basically? Or there's no?
I think you probably should ask Jeremy about than me. Well, did you ask him this question?
Well, I mean, I think someone
Yeah, the same question was asked, but it's good to get your response as well.
Well, I mean, there is similarity. Both generate code, right? So, I mean, I know that's. I mean, I know it doesn't run on. I mean, I know in the compile time, it runs code and generates code which can be saved in the file, and maybe later type check it. But you can also, I mean, I know with a run environment, you can actually run it right away. So MetaOCaml, what it also can do, that there is offshoring facility, which I haven't told you about. So you can generate, I mean, after generate the code, and the code is, I mean, simple enough, which is often it is, you can get C code or, I mean, WASM code and some other things. So it actually can generate, I mean, even, I mean, it looks like generating OCaMl code, but eventually you can generate C code or maybe WASM code. And we actually generated C code. And actually not C code itself, but we can also generate like GPU code, OpenCL, and OpenMP, so supersets of C. So, and then, well, you can, I mean, it's a C code, you can just run it as a C code, or you can run, well, with Jeremy's OpenFFI and, I mean, whatever it's called, C types, and then, I mean, I don't know, dynamically linked and run with the code. So. Oh.
So Edwin asked, does MetaOCaml support threads? What happens if you generate code from different threads? Or is there a lock protecting that global variable?
It's kind of, well, MetaOCaml, I mean, I know I know, I mean, and I haven't actually, I mean, I know it's well, okay, so when, I mean, what MetaOCaml does, as you can see, it's essentially, I mean, giving these brackets and escapes, it generates the code that contains these combinators, as if you wrote those combinators themselves, right? So, I mean, I know there isn't any need for threading, so it's like part of the OCaMl, and, well, it compiles as if there were, I mean, those generators. So, I don't know why, I mean, you need, I mean, I don't know. But also, I mean, I know, well, usually code generation is hardly ever, I mean, kind of time sensitive, right? So you probably want more interested in that generated code runs fast, right? And
sure. So I think possibly the question is whether anything goes wrong with type checking, because you have some global state, whether anything goes wrong if you simultaneously generate code from different...
But, well, I mean, if you look at the type checker, then there is, I mean, more than one piece of global state. There is, I mean, the whole type tree or the type representation is imperative because of the cache. So there is, I mean, yes, and unifier itself is imperative. Then every step of the type checker is imperative. Then I don't know. I mean, hardly actually make it worse.
Okay, well, I think we're out of time, really out of time at this point. So let's thank Oleg again.